This video lecture is meant to cover the information found in Chapter 9, Section 2, which is meant to help you understand how to name ions. This is going to be handy in helping you to recognize and name ionic compounds. So let's start with that. Ionic compounds, of course, always contain ions, and ions can be either cations and anions. Cations are almost always metals, and they are always written first in a compound, both in the formula and in the name. Anions are always nonmetals, and they're always written second, both in the formula and in the name. So if you were to look at if I showed you CO2 and I asked you, is this compound ionic? Well, you'd have to look at these elements on the periodic table and decide, are they metals or are they nonmetals? So if you look up carbon and oxygen on the periodic table, they're going to be found in the upper right corner, making them both classified as nonmetals. So from this, we would conclude that this compound is not ionic. We're going to find out in the following chapter that this substance is indeed covalent. Sodium is a metal. Chloride is a nonmetal. Metal and nonmetal combination, we can conclude that this compound is ionic. So looking at the formula NaCl, you should recognize it as an ionic compound just from the combination of a metal with a nonmetal. Now, becoming familiar with the names of ions, you have a handout which breaks down the ions into 4 particular groups. The first group is a monoatomic cation. Monoatomic meaning single or one atom in each of these ions. So if we have here lithium, sodium, and potassium, both of which have a +1 charge, notice where they are on the periodic table. They are both in the first column, the alkali metals. Alkali metals have 1 valence electron, and so when that 1 valence electron is given away, the resulting leftover charge on that atom is a +1 charge. If we were to take a look at beryllium, magnesium, calcium, strontium, and barium, and find those on the periodic table, we would find them in the alkaline earth metal column. All of those atoms have 2 valence electrons, so when they give up their 2 valence electrons, what's left is a +2 charge. So beryllium, magnesium, calcium, strontium, and barium, the alkaline earth metals, all have a +2 ionic charge. Now if we look at aluminum, aluminum has 3 valence electrons, and so when it gives away those 3 valence electrons, it's left with a +3 charge. Zinc is a +2, silver is a +1. Now, we didn't really talk about valence electrons in this D block, but what's kind of handy is if you can know that aluminum's a +3, diagonally down, zinc's a +2, diagonally down, silver's a +1, +1, +2, +3. Now take a look at their names. Lithium. Lithium did not change its name. So when we're referring to the ion form of this element, we most definitely have to tack on the word ion at the end to distinguish it from a lithium atom. So cations typically do not change the name of the element. You just write out the name of the element and then you tack on the word ion at the end. The second batch of ions are the monoatomic anions, the negative ions. And if we take a look at these, we will see that fluoride, chloride, and bromide, as well as iodide, the halogens, all form -1 ions. These halogens all have 7 valence electrons, so if they gain 1 electron to have a stable 8 octet of electrons, then it'll have an extra electron, and it takes on what we call a -1 charge. Oxygen and sulfur have 6 valence electrons, so if they gain 2 electrons to have a stable octet of electrons, they'll have an overall charge of -2. And then we see the nitride ion with 5 valence electrons. Well, it's going to gain 3 electrons to get a stable octet. And when it gains 3 electrons, it's going to have a -3 charge. Now notice what we did with the names. We took the name like fluorine, or chlorine, and we change the ending of that element to ide, IDE. So fluorine became fluoride. Oxygen becomes oxide. Sulfur becomes sulfide. Nitrogen becomes nitride. And then, of course, we have to tack on the word ion at the end. So anions have ides for their ending. The next group of ions are also monoatomic ions, but these ions can have more than one possible ionic charge, more than one possible oxidation number. That's a synonym for saying ionic charge. So if we take a look here at copper, copper can either lose 1 electron or 2 electrons. And if it were to lose 1 electron, it would have an overall +1 charge. So we use the Roman numeral 1 to indicate the +1. If copper loses 2 valence electrons, it'll become a copper +2, and we call it the copper Roman numeral 2 ion. Now, iron can either be a +2 or +3, and that means it's either going to lose 2 valence electrons or it's going to lose 3 valence electrons. So if we see here, if it loses 3 electrons, it's going to have a +3 charge. If the iron loses 2 electrons, it's going to have a +2 charge. So the Roman numerals are meant to indicate the overall charge of these particular ions. Cobalt, I see, can do the same thing that iron can do. Iron can be a +2 or a +3, as can the cobalt. I tend to remember it that I like to have 2 to 3 cups of coffee. I try to always come up with silly ways to help me remember things, that these are the charges that cobalt and iron can take. So if cobalt's going to be a +2, we refer to it as cobalt Roman numeral 2 ion. If cobalt's going to have a +3 charge, we refer to it as the cobalt +3 ion. Now tin and lead can both take on a +2 or a +4 charge. So we refer to them as tin 2, tin 4, or lead 2 and lead 4 ions. So for these particular ions, where we have more than one possible oxidation number, you must use Roman numerals to indicate what charge is on the ion. Common mistake, though, that I see is that students try to tell me that the Roman numeral tells me how many atoms there are, when in fact the Roman numeral doesn't have anything to do with how many atoms there are, just the charge on that particular ion. The last batch of ions are what we call polyatomic ions. Polyatomic meaning many atoms. And in each ion, the atoms within the parentheses are meant to act as a single particle with an overall charge. And in fact, those ratios inside the parentheses, you're not allowed to ever change them. That ratio stays very constant for the purposes of this chapter. So what we see here is that one carbon, when it's chemically combined with 3 oxygens, overall that particle, that CO3 particle, has an extra 2 electrons, a -2 charge. Right? So we have carbonate and bicarbonate, and we will see here, well, you might actually notice that most of these are negatively charged. The exception is the hydronium ion and the ammonium ion. Hydronium's a +1, and the ammonium's also a +1. So if you remember that most polyatomic ions are negative, yet that's part of the battle you got to fight here. The name is based on the non-oxygen element. So if we look up here at carbonate and bicarbonate, hopefully you can see that both of these elements are based on the name carbon, which is one of the foundation elements in that particular compound. Nitrate and nitrite both have nitrogen in them, so that's why nitra is the name of these ions. But you'll notice ate and ite. And ite and ate refer to the presence of oxygen in the polyatomic ion. And if you know your ions somewhat, it actually is a naming scheme that the ate version will have one more oxygen atom than the ite version. So nitrate has NO3 and nitrite has Sulfate and sulfite, both based on sulfur. SO4 minus 2, SO3 minus 2. Hydronium is H3O with a +1. This is important for acids and bases. Hydroxide, OH minus 1, also important for acids and bases. And then there's ammonium, NH4 with a +1 charge, and phosphate with a PO4 minus 3. I guess that's it. That's all I have for this lecture today. I hope to see you in the classroom.